All right. So a 95% CI for a population mean is calculated for a random sample of weights, and the resulting CI is from 42 to 48 pounds. For each statement, indicate whether it is a true or false interpretation of the CI. This question is asking, do you really understand what the confidence interval means, right? Do you understand what it's for? Okay, let's see. So 95% of the weights in the population are between 42 and 48. Well, does confidence interval tell us about the actual population's members? No, it only tells us about the population mean, right? And so this is actually not true. We still don't know anything about the actual members of the population. We don't know whether it's skewed, whether it's uniform distribution. We don't know any of those things. The 95% thing would only be reasonable, I guess, if the population was normal and its mu was exactly equal to x bar. That would be the case. So that's not true. What about number 2? 95% of weights in the sample are between 42 and 48. Does the confidence interval tell us anything about the sample? No, we're using the sample to estimate population mean. So we're using the SDOM, right? So we don't know anything about just the sample itself. So that's also not true. What about number 3? The probability that the interval includes the population mean is 95%. This is actually true. Only 5%, there is only a 5% chance that this interval does not contain the population mean. All right, what about number 4? The sample mean might not be in the confidence interval. Well, that doesn't make sense if you look at the picture, because we use the sample mean in order to construct the confidence interval, right? So it's like, of course this is in the confidence interval, so this is just ridiculous. All right, example 3. A random sample of 22 men had a mean body temperature of 98.1 degrees, standard deviation of 0.73. Construct a 95% confidence interval for the mean of the population that this sample was drawn from. Interpret this CI. And just a hint is 98.6 degrees included in this. And this is sort of the average human body temperature. Okay. Excuse me. So we have body temperatures in the world, and we don't know what that population looks like, right? But we're asking, what is the can we construct a 95% confidence interval such that whatever the population mean is, there's a 95% chance that we've covered it? Well, we start by assuming that the mean of the sample, x bar, is the mean of the sampling distribution of the mean, right? So we've done step 1. Step 2 is we have to construct the CI. And so here they give us S, but do we have sigma? No, right? And so we know that we can't use z-score. We have to use the t-score. So let's find the t for this. Well, this is 0.025 chance that we won't find it on this side, and here's 0.025 chance that we can't find it on this side. What is the t-score? So this is the raw score, or the temperature. What is the t-score for 0.025 when the degrees of freedom, right, that's n minus 1, that is, there's 22 men, right? So 22 minus 1, so that's 21 degrees of freedom. So if you look in your book at your student's t distribution, I'm going to go down to where the df equals 21, and I'm going to go across to where it says, 0.025. My table actually gives me this area, so I'm going to look at 0.025 on this side, yeah. And it says 2.08 is my t-score. And that makes sense. It's around 1.96. It's similar, right? And you'll see that as degrees of freedom gets greater and greater and greater, this value becomes more and more close to 1.96. And on this side, we know that it's symmetrical, so I know it's negative 2.08. And so from here, I can construct my CI, right? And the CI is going to be the x bar plus or minus the t-value times my standard error, right? And my estimated standard error here is S sub x bar, right? Because we don't have sigma. And so that's going to be S divided by the square root of n. So that's S divided by square root of n. So let's put in numbers here. So that's 98.1. That's our sample mean, plus or minus our t-value, 2.08, times the S, 0.73, divided by the square root of 22. That's our n, right? And so I'm just going to calculate this in on a calculator. So that's going to be 98.1, and I'll do the plus side first, plus 2.08. Remember, Excel knows order of operations needs to do the multiplication before the addition. And it's 0.73 divided by the square root of 22. Right? All right, so that's the high end of my confidence interval is 98.4. And the low end is going to be, I just changed it into a negative sign, 97.8. So 98.4, 97.8. 98.4, 97.8. So that's my confidence interval. Right? All right. So so when we interpret this confidence interval, we want to say something like this. There's a 95% chance that that the mean of the population lies between these two values. Or another way we could say it is that if we draw samples at random, 95% of those samples will include a mean that will include the population mean in between. 95% of the samples in between this interval will include the population mean, right? And so let's think about this confidence interval. Is it reasonable? Is 98.6 degrees included? That's supposed to be the mean for sort of everybody. And we see that it's not actually. And so maybe this sample is sort of odd because our confidence interval doesn't actually include the mean that we secretly know, for body temperature of people. But maybe, I don't know, men might have lower body temperatures? Who knows? So that's when confidence intervals are helpful. So here's example 4. In a random sample of 1,000 community college students, their mean score on a quantitative literacy test was 310. The standard deviation on this test of all the community college students who have taken it is 360. Construct a 95% confidence interval for the mean of all community college students who have ever taken this test. Okay, so here's our random sample. And their mean, or x bar, so this right here is x bar, is 310. But the standard deviation of all the students who have ever taken this test, that's the sigma, is 360. Construct a 95% confidence interval. Well, the first part of it, we know. Population, we don't know jack. But we are given the population standard deviation. And from that, let's construct the SDOM. Well, given that this n is quite large, let's assume normality. And here, we could find out the standard error, by putting 360 divided by the square root of 1,000. Right? And so here, we could now go into our steps of our confidence interval. First, we assume that x bar is the mean of our sampling distribution of the mean. And here we could use z instead of t, right? Because we have sigma, right? And because of that, we know that this is normal. And so that's going to be positive 1.96 and negative 1.96 in order to construct a 95% confidence interval, right? And so our CI is going to look something like this. X bar plus or minus z times standard error. And that's really, and if you sort of double click on standard error, what you'll find is sigma over square root of n, which is 360. So sigma over square root of n. Right? And so let's put in numbers here. So 310 is our x bar. Our z-score is 1.96. Our sigma is 360. And our n is 1,000. And so let's put this into our calculators. So I'll do the high end first. 310 plus 1.96 times 360 divided by square root of 1,000. So order of operation says it doesn't matter what order you put this, anything that you multiply or divide in. Okay, so that is my high end. 332 is the high scoring end. The low scoring end, the lower bound of my 95% confidence interval, is 287.7. So that's going to be 287.7 as well as 332.3. All right, so the mean of the population, 95% of the time, should fall in this interval. So that's the end for confidence intervals, and actually that's part one of confidence intervals. Hope you join me for t distributions to find out why we use t instead of z sometimes.